Hello friends, so in this lecture we will look at aerodynamics, especially in terms of coagulation, condensation and evaporation. So coagulation basically plays a very important role in removing our indoor source generated particles. Coagulation generally will happen when a particle collides and then stays with the another particle. So occurs when a particle collides and then adheres to another particle. So then you have a bigger particle. The particle mass actually does not change because it just coagulates. So the mass is the same, overall mass of particles in the air, but the numbers have reduced because previously, for example, we had two particles. Now we have one particle. So coagulation does not change the total particle concentration by mass, but reduces it by numbers. So mass remains the same, but the number of particles overall mass of particles in the air remains the same, but the overall number of the overall mass of particles remains the same, but the number of particles has changed, basically reduced. So coagulation will also alter the number size distribution because let us say you had two smaller particles, they join and now we have a bigger particle. So now the number size distribution will move towards bigger particles. We will have more bigger particles in the air. So that's what it says. The coagulation will alter the particle number size distribution towards having a large count median diameter. Coagulation will generally depend on the size of the originating initial particles. So when we have the smaller particles less than 1 micrometer, the Brownian motion, convective Brownian motion, enhancement and van der Waals and viscous forces will be the main coagulation mechanisms. So we have more chance, there is more collision happening between particles, so they are coming together more, and through these number of forces we will have a larger coagulation. For larger particles this does not become that important because we have gravitational settling, or maybe while turbulent motions there may be some coagulation, but for larger we are looking at sort of settling and more maybe in the discrete sense. The evolution of indoor particle number size distribution in an empty environment can just be through coagulation. So we have an empty apartment with only outdoor sources, and so the indoor air will have some particle size distribution, and if the particle size distribution is changing and let us say the deposition is negligible right now, then the only way the number size distribution can change will be coagulation. Of course, if the deposition is faster for particular size ranges, then for those size ranges we will have different particle number size distribution, but in the absence or in the negligible magnitude of deposition, that it will be coagulation which will influence the indoor particle number size distributions. Modeling studies have suggested that there is a large reduction in nucleation and Atkin modes within 20 minutes. So within 20 minutes these particles, the smaller sized nucleation particles, well, either they are growing and then coagulating with the other, like combining with other particles, and as a result the number concentration of larger particles, in this case the particles which are more than 0.15 micrometer, so they have increased in numbers. So our nucleation mode and Atkin modes particle basically will go away and will have, they will have more this size particles. The particle number concentration accumulation mode did not change significantly in that case, but we have large reduction in these particles, and actually they move more towards 0.15. But if you start with the accumulation mode particles, they may not be coagulating. So these are basically different scenarios. When you start with nucleation Atkin, they will form larger particles, but when you don't do that and start with accumulation coagulation is a bit less than the nucleation modes. So coagulation, basically it will contribute to the removal of particles, but that will depend on the initial particle number concentrations and the size distribution together. In general, coagulation will play a more important role in indoor air dynamic processes when the particle concentration is higher by number, so we have more particles, and generally distributed in nucleation mode. So we have more particles in nucleation mode, because then those particles will sort of come together and coagulation will become important. So coagulation plays a more important role when the particle concentration is high by number, so more number of particles, and mostly in the nucleation mode. Generally, self-coagulation and bimodal, so coagulation in several modes or two modes, can be ignored when total particle number concentration is below 3000 particles per centimeter cube, because then we don't have enough particles in a given volume of air that they collide and form a coagulation, or they collide and coagulate. But when we are doing cooking or cleaning, the particle number actually goes much more than this 3000 threshold. So that's what it is written here. The total particle number concentrations of indoor particles can reach more than 10 to the power 5 particles per centimeter cube due to indoor sources such as cooking and cleaning. So in these cases, we are looking at coagulation becoming important, or coagulation taking place. Thus, coagulation becomes more important in these settings. Now, coagulation of course depends on a number of factors. This could be particle properties, the indoor-outdoor exchange rate, also the ventilation systems, how strong are the sources which are emitting these particles. Then again, as previously, the building characteristics, which will affect both the concentration and the size distribution through particle loss due to deposition on surfaces. So when the particle is lost due to deposition, then of course there is less chance of coagulation of that particle which was lost. So there are different intrinsic and extrinsic factors involved. If we compare coagulation and air exchange rates, in case of coagulation rates of ultrafine particles that were emitted from gas and electric burners and ovens, the coagulation rate for the smallest particles, so less than actually 0.015 microns, so less than 15 nanometer, was up to 13 per hour within 2.5 minutes of the release, which was much higher. So we see 13.5. This is much higher than the typical air exchange rates for this test house, which is 1 to 0.3 per hour, as we have also done previously, that the typical air exchanges rates are lower, which is 0.1, maybe 0.5, definitely not more than 2 per hour, so like not more than 2 flushes per hour. But we see here that the coagulation rate is like orders of magnitude high. This is also higher than the theoretical deposition rate of these particles, which was about less than 0.5 per hour. So again, coagulation actually is the most important source of removal of this size number from the overall particle size distribution. So coagulation and deposition losses of particles released from 5 indoor sources were studied in a undertaking. These were a gas and an electric stove, a candle, a hair dryer, and a power tool. This was done in a residential test building under different ventilation modes. So that is our setting. gas and electric stove, candle, hair dryer, power tool in a residential test building under different rates of ventilation. For the indoor ultrafine particle releases, coagulation was the major loss mechanism. As we have seen also in the last few slides, coagulation is really important for the ultrafine particles, and this is what this study also found, that for indoor ultrafine particle releases, coagulation was the major loss mechanism. The deposition becomes a significant loss mechanisms as for coagulation when the mechanical ventilation systems were in operation, because then some of these particles will get more deposited on the vertical and horizontal faces. Because the ventilation increased, the airflow became faster and there was more chance of contact between the particle and the surface, which led to more deposition. But if that was not the case, coagulation would have been more important. So in another study, coagulation and deposition were evaluated. In this case, for the diesel exhaust combustion and paper ash particles in an enclosed chamber, and it was found that deposition only accounted for 10% of the particle loss without stirring, but up to 80% of the particles were lost when the stirring was introduced. So the stirring basically increased the contact of air which had particles with the surface, and this led to more deposition. Now when we look at evaporation and condensation, we will look in the terms of also gas particle partitioning. So when the vapor is supersaturated, the particle will grow in size, and then the vapor will condense on the particle surface, and of course this also has implications for the kinetics of indoor aerosols. So particles will grow in size when vapor is supersaturated, and the vapor then condenses on the particle surface, which influences the kinetics as well. Under humid conditions, some types of indoor particles will take up water vapor if they are hygroscopic. So they have a tendency to sort of absorb water, and this will happen more when the conditions are humid. So some types of indoor particles will take up these water vapor, and then they will grow in the size, and this is basically can be termed as the hygroscopic growth of assorted indoor aerosols. In case of some microbes, for E. coli and Bacillus subtilis aerosols, they grew in size by 1.34 and 1.6 times the original value when the relative humidity became more than 85%. So basically they had some hygroscopic properties, and this hygroscopic growth of any particle is a function of its dry diameter. So the diameter when it had no moisture, the aerosol had absorbed no moisture, and the relative humidity, and it has been generally seen that the larger particles sometimes will be more hygroscopic, but of course not hard and fast rule, but this is generally seen. This condensation of water vapor can also take or also play an important role in the health impacts, because when we inhale these aerosols, they will encounter very humid conditions inside our airways, up to 99 or more than 99% in the respiratory tract. So when the particles or these aerosols are inside, and if they are hygroscopic in nature, they will basically become bigger, and then it will influence deposition. Maybe they will deposit. So these hygroscopic aerosols also have implications for human health, because as soon as they go inside, they will sort of absorb moisture and grow. This was condensation or growth by absorption of moisture. The other thing is the evaporation of particles. So when the volatile molecules, let us say we have some particle and the volatile molecules are on the top of these particles, and when they vaporize, the particle size will shrink because the top part is gone. Now we are not talking about 100 millimeters, but some nanometers. These volatile molecules will vaporize, and we are left with the particle. So particles will be shrinking in size with the evaporation of volatile molecules from the surfaces. The volatile aerosols, these volatile aerosols could be from many indoor combustion sources such as cooking or biomass burning. In terms of outdoor, they can have outdoor origins such as traffic generated aerosols, or they can also be secondary organic aerosols. So these are the kind of volatile or semi volatile particles we are looking at, particles with some volatile component, and if there is evaporation happening, these will vaporize and the particle size will shrink. A large fraction of volatile aerosols are generally associated with cooking activities, and then it has been found that after cooking, so example is a vegetable frying, after cooking the particle concentrations can reduce by 47% because sort of the aerosols will vaporize. So in terms of mass, the particle size is going to shrink. So for example, it can shrink to 0.06 from 0.1 to 0.15. So for the 0.1 to 0.5, the number concentration of these particles will decrease because now they have sort of the vapor part has vaporized and the particle size is decreased. So these particle concentration will decrease and these particle concentrations will increase. In another study, the outdoor ammonium nitrate aerosol was basically, it came in the house, and the transformations of this outdoor generated ammonium nitrate aerosol was investigated. In a typical indoor environment, which is so to speak 20 to 25 in a pleasant weather, the evaporation time would be few to tens of minutes, and again this depends on the temperature and the ammonia concentrations. In another study or another setting, the evaporation loss for the 0.5 micrometer particles was ranging from 0.3 to 18 per hour, and this is actually much greater than the deposition loss rate, which was about 0.12 per hour. So 0.12 is much lower than 0.3 to 18 per hour, and this 0.3 to 18, there is a lot of match with the ventilation typical to high ventilation rates, which would be 0.3 to 6 per hour. So 0.3 and 0.3 is actually a similar number. So evaporation loss can become as important as the ventilation and more important than the deposition for compounds such as which are volatile in nature. It is also the main process by which secondary organic aerosols are lost. Again, we are talking about organic aerosols, so the organic volatile component will vaporize. So evaporation could be a main process. There was a measurement of evaporation kinetics of secondary organic aerosols, which was formed by the ozone reaction with apinin and limonene. And it was found that almost 30 to 70% of the secondary organic aerosol mass was evaporated within 2 hours. So the secondary organic aerosol, the organic part or the organic part which was vaporizable, vaporized, which was in this reaction. So for the SOS formed by these reactions, so there was lot of vapor fraction and it vaporized. So 30 to 70% of the mass just vaporized. So that's a substantial decrease in the overall aerosol mass. Of course, then we are talking about evaporation loss. It depends on the relative humidity, the temperature conditions, and also the type of secondary organic aerosols, because if the secondary organic aerosols has more vapor fraction and associated more vaporizable fraction, the loss will be more. So for example, the secondary organic aerosols formed by ozone apinin reactions were more volatile than those formed with ozone toluene reactions. So this SOAs will experience more vaporization and more particle mass loss compared to SOAs that were produced with these reactions. When it was evaluated, the evaporation process was evaluated for the traffic generated submicron particles. Now the submicron particles, a high fraction of the volatile compounds are in the nucleation mode in these traffic generated particles, and the accumulation mode had more non-volatile. So again, immediately we can see that the more particle loss from evaporation will occur in the nucleation mode, and that's what it was seen, that higher loss for particles due to evaporation was occurring at 0.03 micrometer, with the evaporation loss rates almost as high as 1.4 per hour, which is a quite high number, or as comparable to our ventilation rates. Now this evaporative loss was much higher than the accumulation mode particles that had a much lower evaporation rate, about 0.25. So it's almost 5 times lower. And this was, again, as we mentioned earlier, this was because we had high fraction of volatile organic compounds in the nucleation mode in these traffic generated submicron particles, and the non-volatile compounds were more in the accumulation mode. Therefore, we had more volatilization loss for these smaller particles. Now, when we are looking at particle formation, there are two mechanisms, and we have touched this because one is the homogeneous nucleation by condensation of low volatility organic compounds, and the other is the heterogeneous. So, condensation of low volatility organic compounds on the pre-existing particles. So, heterogeneous means pre-existing particles, and condensation. Homogeneous means like the same particle, they are coming together and growing. So, that is homogeneous. Now, when we are looking again at particle formation, the semi-volatile products resulting from surface reactions may be bound to surface, because these are surface reaction, and then they must partition in priority order as surface to air to particle phase to form an SOA. So, something which is in surface, attached to surface, it has to come to air, then have some reaction, and then go to particle phase to form an SOA mass. Whereas those produced from gas phase reaction will only partition to air and then on to the particle. So, if it already exists in air, it will partition to the particle phase, and your secondary organic aerosol is formed. In general, indoor ozone is a major oxidizing agent in chemical reactions that will form indoor secondary organic aerosols. And the principal source of this indoor ozone is from outdoors. So, we have looked at this in this outdoor-indoor lecture. So, this ozone comes inside and then reacts reacts with the existing compounds to form indoor secondary organic aerosols. Sometimes this ozone can also be generated from indoor sources themselves, which are photocopiers, laser printers, electrostatic air filters, and electrostatic precipitators. So, in these cases, the ozone is generated within the environment and then leads to the reactions and forming of indoor SOS. Other important oxidants that will influence or that help formation of SOA are our hydroxyl radicals, nitrate radicals, secondary ozonides, and hydrogen peroxide. So, these are strong oxidizing agents which lead to the formation of secondary organic aerosols. Now, new indoor particle formation thus is directly affected by the levels of oxidants and the SOA precursors. So, the more the oxidants and precursors, the more the formation of SOAs, then humidity and temperature. This is indirectly affected by other room conditions, which could be filters, ventilations, and recirculation systems, which will influence the presence of SOA precursors or the presence of oxidants or humidity or temperature. The secondary organic aerosols by both number and mass are formed less at high recirculation rates. This is because we have the lower concentration of SOA precursors and a higher deposition of SOAs on surface. So, because you have high recirculation rate, the concentration of the precursors would be lower because they might be depositing more to the surfaces, or maybe ventilated out, or less chance of reaction, and the SOAs will be depositing more on the surface. Building surface and furnishings also have a very direct effect on the SOA formation, especially by especially formations that are driven by the surface reactions, because the more the surfaces are available, the more the furnishing is there, the more the surfaces are available, and then we will have more surface reactions possible, and therefore more SOS formation possible. These surfaces and furnishings also influence indirectly, because they will release some volatile organic compounds. So when these, like paintings, varnishes, these VOCs are emitted, these VOCs are oxidized, and then SOS can be formed. Sometimes SOA formation due to surface reaction could occur more favorably on non-reactive surfaces, in the sense that here non-reactive surfaces would mean that the deposition is lower, because because an endo surface coated with an organic film could increase the original reactions on these materials and reduce the formation. The level of indoor aerosols may be even higher with the greater contribution of outdoor particles, if of course the house is located in a polluted area. So then if it's located in a polluted area, more of it will come inside. And then we have seen this, that particle size distribution in empty apartment could be dominated by the outdoor source, and sometimes it can be dominated by nano size during rush hours, probably because of the nature of source in this particular study. And this particular study, it was found that the coagulation rates of nucleation particles, which in this case was 0.02 micrometer, was up to 0.4 per hour, and it contributed almost 20% to the total particle loss. So that is a substantial contribution. It is a non-trivial contribution. So in summary, in this lecture we have seen that coagulation is an important process governing the dynamics of smaller azoparticles, generally less than 1, and more importantly less than 0.1 to 0.2 micrometer. The contribution to removal of such processes also depends on the prevailing airflow condition, and this can generally with respect to deposition on surfaces. For example, if the airflow conditions enable more contact of surface and air, the more particles may just deposit, and maybe then there is less chance for coagulation. Condensation is important because it leads to particle growth and affects the deposition of the grown particle, and also it has some health implications, because the hygroscopic particle, when it goes in, it will sort of absorb moisture and become bigger and then deposit in the inner respiratory tract. Then we know that evaporation of volatiles can reduce the particle size. For example, if the volatile part is on the top of the particle, if it vaporizes, the particle size reduces, and then the new particles can also be formed by surface and gas phase reactions in indoor environment. So this concludes this lecture, and we will carry on in the next lecture.